it's my great pleasure to introduce today's speaker, Dr. Dan Kwang Rocky Nguyen, a senior application scientist at POC Systems Corporation. Dr. Rocky has been pivotal in advancing a nanoscale characterization techniques, particularly in imaging spectroscopic ellipsometry known as ISE and atomic force microscopy AFM. His work has enhanced the precision of measurements at the nanoscale and contributed significantly to solving complex technical challenges in the field. In today's presentation, Dr. Rocky will be discussing how combining ISE and AFM techniques provides a comprehensive understanding of van der Waals heterostructures with a special focus on trapped bubbles and their impact on the optical and electronic properties of twisted bilayer graphene on hexagonal boron nitride. These microscopic trapped bubbles act as local optical cavities, modifying the refractive index and absorption properties of the material, which is critical for applications in optoelectronics and photonics. So without further ado, please join me welcoming Dr. Rocky Nguyen.
Thank you, Cherry, very much for your kind introduction. So my name is Rocky. I'm working at POC Systems Korea. So the title of my presentation today is Investigation of Optical and Electronic Properties of Trapped Bubbles in van der Waals heterostructures based on the combined IC and AFM techniques. So I will be talking about how to study the optical and electronic properties of the sample based on the ellipsometer and AFM. So my talks consist of four major parts. Firstly, I will give an overview on the ellipsometer and AFM, and then I will show an example of combined ellipsometer and AFM study on the van der Waals heterostructure materials. And finally, some concluding remarks will be made. So let's move on to a brief introduction on imaging spectroscopic ellipsometer. So as you may know that the thickness and the optical properties of thin films are very critical that can directly affect the performance and reliability of the micro and nano electronic devices. And as the features are getting smaller and smaller, like MEMS or NEMS devices, the conventional methods are not capable to measure those properties properly at the nano structures. For example, we have some MEMS devices or some waveguide, which is in the very small scale, micro or nano scale, which is typically not accessible by the conventional characterization method for optical or thickness. So in POC system, we're using imaging ellipsometer. So imaging ellipsometry is an optical non-contact tool that can allow measurement of the thin film thickness and optical properties with the very low vertical resolution down to 0.1 angstrom and extremely low lateral resolution down to a single micron. So you can see in this example, this is the imaging ellipsometry measurement on a micro pattern, silicon dioxide on the silicon substrate. And thanks to the high lateral resolution, we can reconstruct the surface of the pattern in terms of 2D or 3D formats, very easy. So let's talk about the ideas or some basic principle of ellipsometry. So in ellipsometry measurement, the polarization state of the light changes when beam hit the sample surface and reflected. And this change in polarization depends on the optical properties and the thickness of the sample. And by monitoring the polarization change, we can apply the optical modeling so that we can obtain information on the optical properties such as refractive index, extinction coefficient, or dielectric coefficient, and also the layer thickness of the samples. So the basic principle of the ellipsometry is that the reflected intensities of the incident beam are recorded at different polarization states. And after that, the polarization properties is converted into the phase shift or delta or amplitude change or psi. And when we have set or different sets of delta and psi at different wavelength, we can calculate the optical properties of the sample. And also, imaging spectroscopic ellipsometer allow the measurement at different wavelength from UV to near infrared, or we can characterize at different angles of incident. So when we have delta and psi, we apply the optical model to this data, and after that, we can have the information on optical properties of the samples, as I mentioned. So let me explain a little bit about the concept of imaging ellipsometry. So imaging ellipsometry combines the measurement capabilities of the conventional ellipsometry and the imaging capability of the optical microscopy. So thanks to this, imaging ellipsometry can image the surface at a very high lateral resolution. So let's take a quick comparison with the conventional ellipsometry technique. So if you use conventional ellipsometer, even with the very high-end microspot option, we can reach out to about 50 microns lateral resolution. And if we use imaging ellipsometry, we can go down on the way to 1 micron in the lateral resolution. So we can see much smaller features on the sample surface. So to sum up, the benefits of imaging ellipsometry include the very high lateral resolution, and also we can achieve as much as 300,000 results or more in one single measurement. And also there is no AY spread thanks to the collimated parallel beam. So that's all for the overview for the ISE. Let me explain a little bit about the Atomic Force Microscopy, AFM. So AFM is a family in the scanning probe microscopy, and everything started as the STM, scanning tunneling microscopy. And STM can only measure the conductive sample in a vacuum environment. And few years after invention of the STM, the atomic force microscopy was born. And AFM is much better compared to STM. AFM allowed the measurement in various environments. And also there is no limit on the sample type. You can measure whatever sample, like insulator, like conductor, or semiconductor. And also with the AFM, we can measure surface topography. We can also measure the electrical, mechanical, magnetic, or various properties such as the thermal properties of the materials. So to understand how small an AFM can see, let's make a quick comparison. So if we have like a wafer with some smaller chiplets on it, with naked eye, we can barely see anything. And if we put a sample on an optical microscopy, we can see a little bit better because optical microscopy allows up to 1,000 times magnification. And if you measure this sample with an electron microscopy like SEM or TEM, we can reach up to about 10,000 times magnification. However, electron microscopy can only measure in the vacuum environment, and also the information on the sample is limited to 2D only. So with FM, we can reach out to a billion times magnification down to nanometer or even sub-nanometer. And also, AFM collect the information on the sample in 3 dimensions, which allow much more insight into the sample analysis. So the idea of an AFM is the atomic interaction. So we can understand this interaction based on some model like the Lennard-Jones potential, which explains the interaction between atoms and molecules. So in this case, the foremost atom of the AFM tip and the foremost atom of the sample surface. So according to Lennard-Jones, the two atoms will attract each other at a far distance, and they will repel each other at a very close distance. So by selecting the tip and sample distance, we can control the measurement in typical like contact AFM measurement or non-contact and tapping AFM measurement. So contact, non-contact, and tapping are the basic imaging mode of an AFM. So the heart of an AFM probe, how does it look like? So you can see here, this is an overview of the AFM probe. This very big part, very rectangular part, is the chip, which is used for cantilever handling. And at the very end of the chip, we have the AFM cantilever. And at the very end of the cantilever, this is the real AFM tip. So the part that interacts with the sample surface during measurement is the very end, the tip end, like this, very small, tiny. And typical AFM probe, AFM tip has the curvature radius at the tip end of about 7 to 10 nanometer. So let me explain a little bit about some basic components of an AFM instrument. So we have the X and Y scanner that moves the sample in the X and Y direction. And on the vertical direction, we have Z scanner. This one will control the tip and sample distance during measurement, and also it controls the atomic force interaction. So to detect the interaction between the tip and the sample, AFM use an optical level detection system, which consists of an SLD, superluminescent diode, the photodetector, and the cantilever itself. So the beam, the laser beam from the SLD, will go to the back of cantilever and reflect it to the photodetector. And the feedback control, the feedback mechanism will adjust the sample and tip distance during measurement, depending on what mode it is. So AFM can be used in various cases. It can measure various properties from very basic imaging modes, such as contact, tapping, non-contact, to electrical modes to measure the electric surface force, to measure the surface potential, or the piezoelectric properties of the sample. Also, AFM can sense the mechanical properties of the sample in various modes. Also, there are some special modes for measuring the electromechanical, magnetic, and various others like thermal properties of the sample. So we have just finished the overview on the ISE and AFM. Now let's see how do we combine those two measurements, those two instruments to study the vulnerable heterostructure sample. So in this study, we prepare a tested bilayer graphene on the HPN sample. And the procedure is just a common dry transfer technique in which a stack of the two layers of graphene on the HPN was prepared on the polycarbonate film. And after that, this stack is transferred to the ion-coated PDMS substrate. After transferring, this polycarbonate film is removed using NMP solvent, like this. And then this entire stack is flipped and transferred to the final silicon substrate for measurement. So after peeling off the PDMS film, we have the sample like this. So this is the sample used for IC and FM measurement. So at the center, you can see the optical image of the sample. So we have the very big HPN flake, and we have the bottom single layer graphene, the top graphene, and this graphite piece is used to apply the current for conductive FM measurement. So I will explain more details later. So for the measurement, we use the accurate EP4 ISE to measure the laser thickness and optical properties. And we also use an automated AFM FX200 to study the Moiré superlattice that is formed by the mismatch between the two top graphene layers. And one major application of these 3D materials is the optoelectronics, such as like photodetector or light emitting diode. So that is the reason why the optical and electrical properties of these materials is critical to understand. So let's briefly look at the setup for IC measurement. So in this measurement, we use accurate EP4 ellipsometer equipped with a 20x objective lens. So this setup allowed the resolution down to a single micron in the lateral direction. For the measurement mode, we use a very popular rotating compensator ellipsometer method, in which the polarizer and analyzer angles are fixed during measurement, and the compensator will be rotated. And during this rotation, the intensity of the light is obtained. And after that, we use the Fourier transform to convert this intensity into delta insight for optical data analysis. And on this corner, this is the layer structure of the sample. So this is the SL2SI substrate, something very common. And on top of it, we have HPN, following by two graphene layers on the top. And about the conductive AFM measurement, we use a diamond-coated conductive AFM tip, and we put a small amount, very small amount of the sample bias, and this part will be transferred to the graphite and to the top graphene layer, and the AFM tip will sense the current on the sample surface. After that, the current signal will be sent to the current amplifier for data acquisition. And since this is fragile materials, we only need to apply a very small amount of contact force. Just a few nanonewton is enough. So this is the IC measurement result on the entire flake. And this is just an example of the data map result at the 400 nanometer wavelength. And when we take a look at the zoom in image, we can see a few spots, a few red spots occasionally occur on the HPN flake, like this. And also on the very top of the bigraphene layer, there's also a little bit, there's also one big spot. And I should note that from the optical image, even with the contrast mode of the optical microscopy, this spot can barely visible. So the reason for this spot to occur is that during sample preparation, we use the NMB solvent to clean up the polycarbonate film. And however, it is not possible to 100% clean up without any trace or residue. So after cleaning, there's some residues, some trace of absorbed water or hydrocarbon on the HPN substrate. And when this entire stack is transferred to the silicon, it will cause some bubble form at the interface between HPN and underlying silicon substrate. So let's take a look in more details. In here, I define the region of interest for optical modeling as R1, 2, 3, and 4. And I built 4 different optical models so that we can independently measure the thickness of the silicon dioxide layer, HPN layer, 2 graphene layers, and also we can characterize the thickness of the hydrocarbon layer. So on the right-hand side, that is the data and size map with respect to the wavelength from 380 to 800 nanometer. And you can see there are 2 major resonance peaks at about 400 nanometer and about 570 nanometer. So comparing our train for without the bubble and with the bubble, we can see there is a horizontal shift about few nanometer in the wavelength for both delta and psi data. So this suggests a different change when we have the bubble below the surface in terms of the optical properties of the graphene layer. So let's see the optical model fit results. So this table shows the thicknesses of all the layers. So the optical modeling allowed measurement of the thickness of graphene, HPN, hydrocarbon, and also we can see the silicon dioxide thickness. And the thickness of the 2 graphene layer is 0.7 nanometer, which is in a very good agreement with the theoretical value of the graphene. Also, the hydrocarbon spot hydrocarbon bubble thickness is about 7.3 nanometer. So as I mentioned before, this change in delta and psi may affect the optical properties of the twisted graphene layer. So to further understand this, I plotted the refractive index and extinction coefficient K, and also I calculated absorbance in terms of percentage. So you can see that when we have the hydrocarbon spot below the surface, the refractive index decreases and extinction coefficient increases. Combine them in absorbance, we have this kind of shape in which below 550 nanometer in the wavelength, the absorbance agree with each other, but above 550 nanometer wavelength, there is a significant difference with and without the bubble below the surface. For example, here at 700, the absorbance is much smaller when we have the bubble below the surface compared when we don't have it. So this suggests a difference in the performance or the efficiency when this symbol is applied as a photodetector. So let's take a look at the FM measurement. So this is these FM images are overlap on the optical image for easier to look. So I confirm the thickness of the HPN flag and also the 2 graphene layers. And for the hydrocarbon bubble with an AFM, we can tell that there is something on the top surface. But since AFM is far less the surface measurement technique, we can only tell that there's something below the surface, but we are not really sure that. But with the epsimeter, we can measure the thickness of that layer like this. But FM, we can see something above the surface only through a few different layers. So in comparison, the epsimeter and FM, in terms of the thickness, they are in a very good agreement. And also a major minor difference in terms of the hydrocarbon is that AFM just take one single light profile on the top surface, and SE can assess below it. So SE can give more or less high accurate result in this case. Also, for typical measurement, the thickness of the thermally ground silicon dioxide layer is very hard to measure using FM, but for ellipsometer, we can easily measure it. So I also did a zoom-in measurement at a higher magnification to investigate the Moiré pattern on the twisted graphene layer. You can see on the RY4 at the very top, we have this shape of the pattern with a periodicity of about 16 nanometer. And here, a little bit offset to the right side, at the RY3, we have a different shape of the pattern with a difference in the periodicity. So this difference immediately occur due to the difference in the stacking registers of the sample or the difference in the twist angle between here and here. And also one more interesting point to note is that although I apply the same amount of sample bus for my 4 and 3, about just 10 millivolt, but the amount of current on the surface is totally different, in which we have about 0.1 nanoamp peak to valley current here. For here on the RY3 is about let's say 0.7 nanoamp, 7 times different. So the main reason for this is that the applied contact force when measuring the RY4 and 3 are different, in which RY4 I apply 5 nanonewton and I double the force at 10 nanonewton for RY3. So that's why we have the higher amount of current. So for more details, the contrast mechanism of conductive FM measurement is the conductivity or the current flow between the junction between the tip and the sample. So if we push the tip harder toward the surface, the contact area between tip and sample is larger and it's allowed more current, more electron to flow. So that's why we obtain a higher signal, a higher amount of current for our tree here. So now let me summarize my talk with a few remarks. So using both combined ISE and FM methods, it increases the confidence in the correctness of the trapped hydrocarbon bubble assumption. And also the result allowed a deeper understanding of the properties of the heterostructure sample from the microscopic view on how the sample interacts with the incident light to the nanoscopic view on the morphology and electrical characteristics of the sample. So we believe that its synergic combination of ISE and FM can allow a deeper understanding of complex surface system. So this is the end of my talk. Thank you very much for your attention.